Hello everyone, my name's James Pruitt. This is my first lecture in a series of lectures on JavaScript. I'm not going to do the standard teaching a language uh, uh, format. I'm going to construct a computer algebra. What I'm trying to do with my website and my YouTube is learn mathematics and teach mathematics. And so I'm going to construct a computer algebra system, and I'm going to do that using JavaScript. And I've chosen JavaScript because it gives me access to the Firefox browser, which has a mathematical typesetting system built in. Um, Later on, after I get through my computer algebra system, because I want to get that done right up, I don't want to wait wait too much longer. Later on, once I get my computer algebra system going, I'm going to approach JavaScript properly, to teach the language properly, and that entails constructing a computational model to describe the process as it evolves. When you look at a computer programming language program, it's not really, the program is not the process. You want to make the distinction between the program and the process. The process is that's what's going on inside the computer or the browser or whatever software that's running on the computer. The program directs that process, and to truly be a good programmer, you need to be able to have an idea of how that process evolves. And what you need to, in order to do that, you need a model, a computational model. But that's going to take a while, and I don't want to get bogged down into that. But I'm going to come back and do that. Right now, I'm just going to plug through, try to describe what I'm doing as I'm writing my program, my computer algebra system. And what distinguishes a computer algebra system from a numerical analysis and other math is that computer algebra is about symbolic. It's not about approximations. Numerical analysis is about approximations, and so closeness is not important for us in computer algebra. In order to do a specific, not dealing with approximations, you need a large integer. You can't have a fixed size integer. You need a multi-precision integer. You can't say, well, 64 bits is enough. You need to just keep growing that to whatever size you need until you run out of memory. So that's the first step we have to do, is to develop a large integer type, an integer type that grows. And with JavaScript, the only number type JavaScript has is what's called a double. JavaScript is syntax is derived from C, and a double is a IEEE 754 format. It's a 64-bit floating point number. So that's all they have. And so when we have, and the only operations we have is multiplication on doubles, addition on doubles, subtraction, etc. So that's what we have to build. That's our primitives from which we build our large integer type. First of all, though, I want to talk about integer types. And what you're going to do is you're going to have to have a radix. A radix is a base system, is the base. A radix is the base of the number system. So for the decimal number system, the base or the radix is 10. For the binary, it's 2. So we have to choose a radix to do. So that's to define our number system. So we're going to have like let's see how I want to write this. So if I have A1, A2, actually let's erase this. This is not what I want. So if I have say for instance A3, A2, A1, A0. This is a number. This is how we represent numbers. And for depending on the base we use, this number is going to be A3 times, where B is the radix, or the base, to the third, plus a2b squared plus a1b b1 plus a0 b to the 0. And we're going to have all our an. The magnitude of an is going to be actually we're going to have a separate digit for negative. So all these an's are positive. So our an's are going to be greater than or equal to 0 and less than our base. And so if this is a decimal number, the b is 10 cubed, 10 squared, 1,000, 100, 10, 1. If this is a binary, this is going to be 8, 4, 2, 1. So we have all our standard algorithms of addition and multiplication and division depend on this representation. So what we're going to do is try to figure out, we're bound by that double, and we have to figure out what our base is going to be. And we're going to decide on how large a number we can represent with our primitive number type, our double, and then we're going to use that, and we're going to derive from that our large integer, and we're going to use the basic algorithms of addition and multiplication using this representation. Okay, so let's go in and talk about our IEEE 754. This is what Java uses. IEEE 754 double. This is JavaScript's only data type, only number type. And they have other data types. And they have addition, multiplication, etc. defined on this number type. And the IEEE, if you want to look it up, I have it on this website. You go up to Google it, and you're going to you can look at the Wikipedia, and they'll describe. I don't know if they want me to show their web page. I don't know if I'm violating copyrights. I apologize if I am, and I'll take it down. But you look up the Wikipedia page. It's IEEE 754. It's the 1985 version. You come down to the double precision 64-bit, and this will give a complete description of your IEEE 754. But let me describe what we need to know. Let's see. Okay, so what you got, this is our number, this is our 63rd bit, this is our 0 bit, this is a 64-bit number, this is 1 bit, and this is the sign bit. And if it's 1, that means the number is negative. If it's 0, that means the number is positive. And then you're going to have 11 bits here, and this is called the exponent. And then we're going to have 52 bits. This is called the significand. And how this works is we don't need to know all the details about this, but if we look at the exponent, this number 2 to the 11, if you take 2 and you multiply by, you raise it to the power 11, 2 raised to the power of 11 is 248. You want negative and positive exponents, so you're going to have to cut that in 2. So that's 1024. So if you look at this right here, 1024, and I'm not sure of all the precise way this works. So you can have up to positive 1024 to negative 1024. But what they do with this is, if all these are positive, you're going to get what's called, either if all these are positive and this is 0, that's going to be and this is 0, you're going to get a positive infinity. If this is 1, you're going to be negative infinity. If this has any number besides 0 in it, and these are all 1s, you're going to get what's called not a number. And I think JavaScript represents it that way. So there's 2 to like 53 not a number values. And JavaScript lumps them all into 1, and we're not going to worry about that right now. And you have 2 infinities. If this is all 0 and this is plus and minus infinity, if that's all 1s. So you subtract, you got one little 0 here, all the way down to all 0s. If all 0s and this is all 0, that's where you get your 0s from. But so you're going to get the exponent can be up to 10 to the 23. So you're looking up to a number that's 10 to the 23. Let me see how we're sitting on time. So this is the largest number because of the nada numbers. That if it didn't have the nada numbers, that'd be 10 to the 24. 2 to the 10 to the 2 raised to 1024. But no, it's 2 raised to 1023. And if you look, and what they do, if this is any value, if this has a number here besides 0, you're going to get you're going to get 2 to, say for instance, if this is 2 to the 100, we're going to raise 2. We can represent that they actually have to represent it. You take whatever number, they have what's called a bias, and I think the bias is 1023. So whatever number you have in here, subtract 1023, that's your number. So if you have your number 2 to the 100, it's going to multiply whatever 52, it's going to append a 1 point to whatever 52 bits here. So this might be 0, 0, 1, 1, 1, dot, 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 whatever's in here, and that's your 52-bit value. And if this is not all 0s, this is how it works. They're going to append this 1 point. So this 1 bit is implicit. So that gives you 53 bits of information here. So that's how they snuck in an extra bit. So that's called a normalized number. And so this is this 2 to the 2 raised to the 100 times this number. So that pushes that decimal point to the right 100 spaces. So this is called a normalized number. So you can have up to 2 to the 53 in precision. So if I have that number, if I have this normalized number, say if I have all 1s, all 52-bit 1s, and say that's my 52 bits plus my extra implied bit, implicit bit. So that's 53. So if I raise this up to the 2 to the 53, if I multiply this number by 2 to the 53, that's going to push, actually 2 to the 52, that's going to push that decimal place 52 places to the right. Now if I go 53, that's going to have a 0 at the end, and I'm going to start skipping numbers. So once I get large enough numbers, my numbers are, I'm going to skip a bunch of integers, and my number system, I have to have consecutive. I got to work with consecutive integers. I can't be skipping integers. It's my system is going to collapse. My large integers. I want to have every integer possible. I don't want to skip integers. I don't want to approximate. So the largest number that consecutive numbers is from 0 to, not counting my plus or minus. Actually it's from negative 2 to the 53 dot 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 to 253. These are consecutive integers. Let me erase this. These are consecutive. I can represent every number with my double with my IEEE 754. Every number between negative 253 to 253. So I'm going to go ahead and stop right now, and I'm going to get back on my next lecture, and so the next one will be posted immediately, and we'll pick up right where I left off here.